So you've got electrical charges. And typically we just have, like, let's say we've got a charge Q1 and a charge Q2. And let's say for simplicity, these are both positive charges. Then what are they going to do to each other?
Repel.
Yeah. If these are both positive, they're going to repel, which means object 2 experiences a force to the right from object 1. This is the force on object 2 from object 1. And likewise, object 1 experiences a force to the left from object 2. So this would be the force on object 1 from object 2. And what should we assume about these two forces? They should be the same, at least the same magnitude, opposite direction, but equal magnitude. Because these are the sort of force pair that Newton's third law is talking about, the equal and opposite forces. Or I usually just think of it as the same force viewed from two different perspectives. One pushes 2 to the right, 2 pushes 1 to the left. But since they're the same amount of force, we don't really need to consider them separately. We can just focus on one of these forces and ignore the other one. And what we usually do for electric forces is we treat one of these objects as what we call the source object. So let's say we call object 1 the source object, or source charge. And we call object 2 the test object, or test charge. And there's no physical distinction between. It's just not like source charge and test charge are two different types of charges. It's just that we're calling one of the objects, one or more of the objects, I should say, the source charge or source charges, and one specific object the test charge. The idea here is we're going to treat object 1 as creating some sort of effect, and object 2 as experiencing a force from that effect. So the source charge creates an effect that we call the electric field. Object 2 feels a force from that field. And when we say field, we basically just mean some sort of effect on the space around it. A field is just something that has a value at every location in space. Like for instance, temperature could be considered a field. Every location in this room has a temperature associated with it. Maybe all the same, maybe some different. But since every location can be assigned a value, the temperature at that point, we would say temperature is a field. Or wind velocity, for instance. If you've got wind blowing through a region of space, every location in that space has a wind velocity associated with it. You could measure the velocity of the wind at that location. And since velocity has a direction associated with it, we would say wind velocity is a vector field, not just a scalar field, but a vector field, assigning a vector value to each location in space. So the idea of the electric field is that the source charge is creating some effect in the space around it, and the test charge is experiencing a force because of that effect. And this is completely reversible. We could say object 2 is creating an electric field as the source charge, and say object 1 is the test charge experiencing a force from it. There's no physical difference between source charge and test charge. It's just a matter of record keeping. So the general approach is we're going to say the source charge creates an electric field, this idea of influence in the space around it. The source charge creates an electric field. And that electric field exerts a force on the test charge. Of course, what's really physically happening is these charges are exerting forces on each other. But it turns out it's mathematically very convenient to treat it as source charge creates this effect we call the electric field in the space around it. And the electric field creates a force on the test charge. Any questions on that terminology so far?
Would an electric field be a vector field?
Yes, because it's the thing that's causing a force, and force is a vector, so it would make sense for the electric field to be a vector also. because we've got to have some sort of directionality there. And to look into what electric field actually means, let's take a look at an example of several charges all experiencing the same sort of thing. Let's say as the source charge, let's say we've just got some gigantic positive charge over here somewhere. So we'll call this the source charge. And usually the source charge is the one we don't really care about forces on. Like this source charge is going to experience forces from other charges we put nearby. But the idea is maybe the source charge is so massive it's hardly going to move at all. Or maybe it's fixed in place by other forces, some sort of structural framework holding it there. Or maybe it is going to move, but we don't care that it moves. We want to focus on some other object, the test charge. So let's say we have a test charge that is positive 6 coulombs. And we call this a test charge in the sense that we're going to put it at this location as part of an experiment to test out what happens at that location. And let's say we put it at this location and we find that it gets repelled with a force. And we can measure this force with a spring scale. Let's say this experiences a force of, let's say, what would be a good value here? Let's say it experiences a force of 21 newtons. So this object with this much charge experiences a force of 21 newtons. And that's just something we would have to measure. But now let's say we remove that charge and we put in a new charge, a new object whose charge is, let's say, 18 coulombs. If we put in, so ignoring this one, if we now put in a different charge whose charge is 18 coulombs, what would you expect to happen to that? How much force would you expect that to get? Presumably 3 times as much. And why is that? Why would we expect this charge to get 3 times as much force? Yeah, 6 times 3 is 18. This is 3 times as much charge, so we should expect 3 times as much force. In fact, this 18 coulomb charge, you could think of this as essentially 3 copies of this glued together. If each one of those copies gets 21 newtons, that's a total of 63 newtons. Force is additive like that. Or alternatively, what if we had a charge that was only 3 coulombs? If we had a charge that's only 3 coulombs, how much force would you expect that to experience? How does that compare to the original charge we were investigating?
It's half as much, so it'd be half the force.
Yeah, half as much charge suggests we should experience half as much force. So that would be 10.5 newtons. Or what if we had, let's say, a charge that was negative 12 coulombs? What force would you expect that to experience?
Going to be double, but going in the opposite direction.
Yeah, twice as much because it's twice as much charge. But yes, in the opposite direction because this negative gets attracted to this positive. So that would be 42 newtons to the left. And we wouldn't call that negative 42, by the way. We'd still call it 42 newtons. It's just 42 newtons to the left because the vector has direction associated with it. So it looks like each one of these charges is experiencing, even though they're all in the same situation, we're assuming we're putting all these at the same location one at a time, they're all experiencing different forces because they have different charges. But note that we've been assuming all along that the force is proportional to the charge. The whole idea that, well, this has 3 times as much charge, so of course it experiences 3 times as much force. Even though we didn't say it in these words, we've been explicitly assuming that the force is proportional to the charge. And it turns out that is in fact true. Electric force, whether it's attractive or repulsive, is proportional to the charge of the test object. Twice as much charge means twice as much force, and so on. And we can always write proportionality as an equation. In general, if y is proportional to x, how do we write that as an equation? Y equals what?
Y equals X?
It's not just y equals x though, because if proportional just meant equal, we wouldn't bother having a separate symbol. It's x modified by possibly what else?
Oh, by a factor in front of it, like a coefficient.
Yeah. If y is proportional to x, then that means y equals x times something, typically x times some constant. Y equals, not yx specifically, but some constant times x. So maybe c times x or k, whatever you want to call the constant, times x. That means if we're assuming that force is proportional to test charge, we should be able to say force equals something times test charge. Electric force equals test charge times something. There's some factor we can multiply by test charge to get the force. And that something is what we call the electric field. So the electric field, this quantity E, can be thought of as the value, the coefficient you multiply by the test charge to find the electric field. Also, since charge is a scalar and force is a vector, what does that tell you about the electric field?
It's a vector.
Yeah, this has to be a vector. So this also establishes the idea that the electric field must be a vector quantity, a vector field. Because if we're saying that electric field is the quantity you multiply by charge to find the electric force, force is a vector, charge is only a scalar. The direction has to come from somewhere. So electric field, this multiplier has to be a vector so that a scalar times a vector results in a vector. So this is essentially where the idea of electric field comes from, that there's got to be some multiplier, you could almost think of this as a conversion factor that turns the charge into the electric force that charge experiences. And that multiplier is what we call the electric field. Any questions on that so far? And anytime we introduce a new quantity, this new multiplier here, a new variable, what are some good things to check about it to investigate it further? What's some other information we could find here? How could we get more information about what E means? First of all, could we figure out what units of measurement it would be measured in? Like, do we know units of measurement for everything else here? What is charge measured in?
Coulombs.
Yeah, charge typically measured in coulombs, and force is going to be measured in what's our usual unit of measurement? Yeah, newtons. Newtons is our usual unit of measurement for force. So in order for this to match up, what does electric field have to be measured in? What would the numerator and denominator here have to be to make this equation work? Yeah, that's got to be newtons over coulombs, newtons per coulomb. So this is one way of writing the units of measurement for the electric field. There are other ways as well by manipulating the units, but newtons per coulomb will work fine for now. And strangely, nobody's assigned a name to that. You would think that at some point in the last 200 years, somebody would have named newtons per coulomb after some dead scientist from the 1800s. But as far as I know, nobody has yet. So it's just newtons per coulomb. But that's the unit of measurement we'll use for electric field. And we can actually calculate the electric field. If you solve this for E, what would you get? How would you isolate E in that equation?
Divide by the test charge.
Yeah, divide both sides by test charge, so we get the force experienced by the charge divided by that test charge itself. Should probably fill in the subscripts there. The electrical force felt by the test charge divided by the test charge itself. So this is a very handy way of defining electric field. This is what electric field is. Electric field is defined as this ratio of how much electrical force the particle feels divided by the charge of that test particle. Note that you can also get the units from this. Force is in newtons, charges in coulombs, so newtons per coulomb. And we can use this definition to calculate the electric field experienced by each one of these. So if we do that, for instance, here we've got force at 21, the charge is 6. If we divide those, 21 newtons divided by 6 coulombs, what does that reduce to? Newtons divided by 6 coulombs. Yeah, 7/2 or 3.5. So we can say the electric field is 3.5 newtons per coulomb. Also, it's a vector quantity. What should the direction be here? If we just take in this vector to the right and we divide by 6, what is dividing? Yeah, it should still be to the right. If you just multiply or divide by 6, you're changing the magnitude, but you're not changing the direction. So the electric field that this particle experiences is 3.5 newtons per coulomb to the right. What about this one? If you take this force divided by this charge, 63 newtons to the right, divided by 18 coulombs, what do you get? Yeah, same thing. 63 divided by 18 is also 3.5. 3.5 newtons per coulomb, and still to the right. And this one, if you divide 10.5 divided by 3, same thing. That's still 3.5. 3.5 newtons per coulomb to the right. Even with this one, 42 divided by 12 is 3.5. And if you consider the signs, if you take a vector to the left and divide or multiply by a negative, what happens to the direction? If you multiply or divide a vector by a negative, what happens? Yeah, it flips. Well, I wouldn't say it flips the sign. I would just say it flips the direction. The negative sign in the multiplier or divisor flips the direction of the result. So 42 newtons to the left divided by negative 12 is 3.5 newtons per coulomb to the right. So when we divide these, a vector to the left divided by a negative sign becomes a result that's a vector to the right. So the result is still 3.5 newtons per coulomb to the right. So all of these objects are experiencing different forces because they have different charges. But the electric field is the same for all of them. They're all experiencing the same electric field because electric field is the ratio of force versus charge. And that ratio is the same for all of them because force is proportional to charge. And this means, although force is a property felt by that particle, this particle experiences 63 newtons of force, that particle experiences 21 newtons of force, but they're all experiencing the same electric field because electric field is not a property of this particle. Electric field is a property of that location in space. Regardless of which particle we put here, we would say, this location in space has an electric field of 3.5 newtons per coulomb to the right. Even if it's empty, even if we don't put a particle here at all, we would say that empty point in space has an electric field of 3.5 newtons per coulomb to the right. And I tend to think of electric field as the ability to cause a force on a charged particle. Even if we don't put anything here, this empty point in space has the property that it could apply a force to a charged particle if one were put there. So that's really why we call the electric field a field in the first place. It's a field in the sense that it has a location at every point, or it has a value at every location in space. And it's a vector field because that quantity has a direction associated with it. Any questions on the meaning of electric field so far?
Wait, just to what you said about multiplying or dividing by a negative, that flips the direction?
Of the, in terms of vector arithmetic in general, yeah. If you take any vector and multiply or divide by a positive scalar, the direction doesn't change, just the magnitude. If you multiply or divide by a negative scalar, the result is in the direction opposite to the original vector. Okay. Any other questions on that so far? And note that this definition gives us a way to convert back and forth between these quantities. If you know the electric field at some location in space, you can multiply that electric field by the charge of some object to find the force that that object would experience if placed at that location. Or alternatively, if you can measure the force that some object experiences, you can take that force and divide by the charge of the object to find the electric field at that point in space. And of course, the electric field is ultimately caused by some source charge. We've been ignoring the source charge so far. We've just been treating it as this point in space has the property of being able to apply a force to charges. But that electric field is ultimately caused by the existence of some source charge somewhere else. And the reason why location is important here, let's say we take all of these charges and move them closer to the source. What would you expect to happen to all the forces if the charges are closer together? Yeah, presumably they would get stronger. In general, long distance forces tend to be stronger if the objects are closer together and weaker if they're further apart. So if you take this 6 Coulomb charge and move it closer to the source, it's going to experience a stronger force. More force for the same amount of charge means a stronger electric field. So we'd say if you're closer to the source charge, the electric field in that region is stronger. If you get further out, the electric fields would be weaker. So the 3.5 newtons per Coulomb is just for this location. If you're closer, it's going to be more than 3.5. If you're further away, it's going to be less than 3.5. And again, this ties into the idea that it is a field. It has a value at each location in space. Different locations can have different values. And specifically, if you're closer to the source, it's going to be stronger. Any questions on that so far? And one equation you're going to see fairly often is the electric field caused by a single point charge. A point source. A point source just means a lump of charge that is it's compact into a small enough space that we can treat it as a single point. So if you just got a single point with lots of charge at that location, you can treat that as a point source. And the electric field from that, at least in terms of magnitude, the usual formula for that is K times Q source over distance squared. And I guess that charge should be considered to be an absolute value because we're talking about a magnitude. K here is just the universal electrical constant. You can look that up if you need it. But usually I would just leave the answer in terms of K unless you need a specific number. Q source is just the charge of that source object that's creating the electric field in the first place. And R is the distance from that central object out to the location of interest. But this just tells you the stronger the source charge is, the stronger the electric field will be, of course. And also the further you are from it, the weaker the electric field gets. And it gets weaker pretty fast as you get further away. This R squared suggests that it's getting weaker very fast. So you get very strong electric field if you're very close, and it gets very weak very fast as you get further away. But note that this never disappears entirely. No matter how far away you are from the source charge, there's still going to be some electric field. It just gets weaker and weaker and weaker. So you can use this to calculate or predict what the electric field will be at any location near any single point source charge. And then of course you can just multiply that by the force on the test charge is just going to be that times the test charge. Electric field times the test charge. And again, I'm putting the charges in absolute value because we're just looking at magnitude. We're not looking at direction yet. And we often, not always, but we often use capital Q for the source charge and lowercase q for the test charge, but that sometimes gets mixed up. Different problems might use different notation for that. But in general, capital Q and lowercase q, often with subscripts, if there's several charges you need to keep track of, can be used for the source charge or for the test charge. But this would tell you the force that one charged particle exerts on the other charged particle. Any other questions on that so far?
Sorry, can you kind of, there's the two equations for finding the electric field, right? And then is that equation in the middle, like how you related the two?
Well, this one is the definition. This is what electric field means in general. So this is what electric field is. Electric field is the ratio of how much force this particle the test particle experiences divided by the charge of the test particle. This formula here is for the electric field caused by a point source. So this is specific to one type of source charge, if the source charge is just at a single location. This doesn't work if the source charge is more spread out. Like let's say instead of just a single tiny point of charge, let's say you've got a bar that has positive charge distributed all across it. In that case, this formula won't work because this formula is specifically talking about a single tiny point of charge. This formula though, this is what electric field means. So this is universally applicable. And then this one right here is just taking the electric field caused by the single point and multiplying by the test charge. So this is just applying the definition that force equals charge times electric field, applying that to this specific formula to get a formula for the force between 2 point sources acting, or 2 point charges acting on each other. So this would be going back to the first thing we were looking at, where you just got a charge here and a charge here, and you want to find the forces they exert on each other. Any other questions on that so far? And let's take a brief look at direction and the notation we're going to use for this, and then we'll get into electric potential, which is related but not quite the same thing. And so far we've been looking at the idea of the electric field causing a force on the test charge. The electric field exerts a force on the test charge. Let's take a closer look at the source charge creating the electric field in the first place. Let's say you've got some positive source charge. And we want to map out what the electric field in this region of space looks like. The electric field is defined as the ratio of force that a test charge would feel divided by that test charge. Even if there's no test charge there, that empty point in space still has an electric field. And the way I usually think of this, anytime you've got something defined as a ratio, what's the easiest denominator to divide by? Yeah, 1, and specifically positive 1. So I tend to just imagine, what if the denominator was 1? If you imagine plugging in 1 for the denominator, then the electric field is the force, specifically the force that would be felt by exactly 1 unit of charge. The force that would be felt by a positive 1 coulomb test charge. So if you're not sure which direction the electric field points in some location in space, imagine what would happen if you put a 1 coulomb test charge there, just a small positive charge. Ask yourself, which direction would that get pushed or pulled? for example, let's say we imagine putting a tiny test charge right here, +1 coulomb. Which direction would that get shoved? Which direction would the force be? If these are both positive, what are they going to do to each other? They should repel, which means this test charge gets pushed in which direction? Yeah, north. North or up or whatever you want to call that direction. So the force on this test charge is northward. Divide by +1 coulomb, nothing changes. So that means the electric field at this location is also northwards. If we put that same charge a little further away, we would still get a northwards force. It would just be weaker and weaker. Or what if we put the test charge here instead? Which direction would the force be? Yeah, to the east or to the right. And the electric field is the force that would be felt by a +1 coulomb charge. So if a positive test charge would experience a force to the east, then the electric field is also to the east. Fairly strong if we're close, and then getting weaker and weaker as we get further away. Or if we put the test charge, let's say here, it's going to experience a force to the south, repelled away. In fact, in general, the electric field is going to be pointing away from this positive source charge and getting weaker and weaker as we get further away. So these arrows would all represent electric field vectors. Electric field. So this would be the electric field drawn as vectors. We're mapping out the electric field vectors in space all around this positive source charge. We just get arrows pointing outwards in all directions. And again, you could think of these arrows as representing the force that would be experienced by a small positive test charge placed at that location, for instance. Of course, drawing out all these arrows can get really tedious. So usually, instead of drawing out the individual arrows, we just draw out the general trend lines. For instance, I'm noticing we get arrows pointing just away in all directions. So usually the way we draw this is what's called a field line diagram. Instead of drawing the individual vectors, we just map out the individual trends, or the overall trends, I should say. For instance, we have just a whole bunch of vectors pointing outwards. So I'm just going to draw a bunch of outwards arrows, evenly spaced, because we should expect symmetry. So this would be the field line diagram. These are not vectors. These are just long lines with a direction associated with it. Or they could be curves. In this case, they're straight lines, but they don't have to be in general. You could have curved electric field lines. But these just represent that, for instance, at this location, the electric field is this way. At this location, the electric field is this way. At this location, the electric field is this way. So these field lines just tell you the general trend of directions of the electric field. And that's usually called a field line diagram. You can do the same thing with gravitational fields. For instance, if you want to map out the gravity of the Earth, you would just have the picture of the Earth and a whole bunch of arrows pointing, or directed lines pointing straight in from all directions. The one problem with this, it's a lot easier to draw, it's a lot easier to interpret, but the one problem with it, what information do you lose when you just connect these arrows into lines? We've still got all the information about direction, but what information have we lost? Yeah, we've lost some information about magnitude. We're no longer showing the size of those arrows, but we still have some information about magnitude, because what do you notice about the field lines close by and the field lines further away? As we get further away from the source, what do you notice about these field lines next to each other? Yeah, they're more separated. They get more spread out. That's how we signify magnitude in the field line diagram. In a field line diagram, if the field lines are packed very close together, that means a strong magnitude. If the field lines are more spread out, that means a weak magnitude. And this is relative. We're not really just showing specific numbers with this. We're just showing closer together means a stronger field, further apart means a weaker field. So you can see visually that you get a strong electric field in the region close to the source charge. You get a weaker electric field if you're further away from the source charge. So it's not really showing it numerically like the length of a vector would, but you can get a general idea of, I guess you could say like number of field lines per square inch or something like that. So that's the field line diagram. It shows direction very clearly of the vectors, and it approximately shows relative magnitudes based on how close packed or how spread out the field lines are from each other. Any questions on that so far? By the way, if this were a negative source charge, what would be the only difference if we had a negative source charge? What would be different about the field line diagram if we had a negative source charge instead of a positive source charge? If we go back to the definition that the electric field is the force that would be experienced by a small positive test charge, yeah, the arrows would just be pointing inwards. Because if this was negative, a small positive test charge would get attracted towards it. So the field line, the electric field vectors, and therefore the field lines, would be pointing inwards towards the negative source charge. And this is generally true of electric fields. If you have more complicated arrangements of charge, like let's say you've got not only one source charge, let's say you've got several source charges, and you want to find the total electric field everywhere, you can do that by finding the electric field at each location and adding the vectors together at each location. And they can get pretty complicated. But as a general rule, the field lines should be pointing outwards from positive sources and inwards towards negative sources. So for example, if you had a more complicated arrangement of charges, let's say a positive source charge and a negative source charge, drawing out the complete field can be kind of complicated, but we know that we at least need to have field lines coming out of the positive charge and going into the negative charge. And what this ends up looking like is something like this. We've got all these field lines coming out of the positive charge and field lines going into the negative charge. And if we add in more detail by putting in more arrows, still evenly spaced. So we got to fill in all the in-between gaps if we fill in any. And this ends up looking kind of like this. So this would be the field line diagram if you have a pair of charges, one positive, one negative. And you can get this by taking a look at each location and saying, what's the electric field caused by by charge 1? What's the electric field caused by charge 2? Add those together and you get the total electric field at that location. Excuse me. Any questions on that so far? And again, as a general rule, electric field lines should be coming out of a positive source charge and going into a negative source charge. You can also occasionally have electric field lines coming in from very far away or going out towards very far away. But most of them should be either starting a positive charge or ending in a negative charge or both. Any other questions on electric fields in general so far? All right, then let's take a brief look at potential also. Let's say you're in the presence of an electric field And let's say we just got a constant uniform electric field, same electric field everywhere. Let's say the electric field is 50 newtons per coulomb everywhere. Presumably this is caused by, maybe there's a wall of positive charge over here and a wall of negative charge over here. But the nice thing about electric field is once you know the electric field, you don't have to care about the source that caused it anymore. The electric field has all the information you need. And let's say we have a positive charge here. Let's say positive 10 coulombs. This would experience a force of how much? How much force would that experience? Or how would we calculate the amount of force? Yeah, it should just be 500 newtons. We can go back to the idea that force is test charge times electric field vector. We've got the electric field vector, we've got the test charge, so we can just multiply those. 50 newtons per coulomb times 10 coulombs is 500 newtons. And since it's a positive charge, that doesn't change the direction. The force is 500 newtons to the right. And so if we just let this go, it's going to drift to the right, getting faster and faster and faster because the force causes acceleration. But let's say we don't want it to accelerate. Let's say we just want to hold this in place. In fact, let's say we want to move it steadily to the left instead. Let's say we want to move this 2 meters to the left. To its new home over here. If you want to move it, or more precisely, if you want to prevent it from accelerating, if you want it to just move at a steady pace instead of accelerating, you've got to apply a force of your own. You've got to apply the same amount of force in the other direction just to keep it from accelerating. So you're applying a 500 Newton force of your own as it moves 2 meters. And what do we call that? If you're applying a force to a moving object, what are you doing to it? What are you applying? Force times distance equals if you think way back to 7a, what are you doing to an object if you apply a force as it moves? Yeah, that is work. Force times distance equals work. So going back to the idea of work being force times distance, if you multiply force times distance, 500 newtons times 2 meters, you get 1,000 joules. Newtons times meters is joules. So over the course of this journey, you're doing 1,000 joules of work. And that work you're doing, work is just a transfer of energy, but you're moving it at a constant speed. So what's the only type of energy you would be changing? It can't be kinetic energy because we're moving it at a constant speed. So what other type of energy could be changing? Yeah, potential energy. The work you're doing is investing potential energy into the system. And specifically, we would call this electrical potential energy because it's associated with working against an electrical force. By moving this on this 2 meter journey, you're increasing the object's electrical potential energy by plus 1,000 joules. If you then released it, it would start falling back towards the original location and getting faster and faster if you weren't holding it back. And that potential energy would be converted back into kinetic energy. However, what would happen if we used a differently charged object? Let's say we used an object with twice as much charge. Twice as much charge means the force is going to be what? Twice as much charge means twice as much force, right? Yeah, we get 1,000 newtons of force. So we'd have twice as much force multiplied by, let's say we take it on the same journey. So twice as much charge means twice as much force means twice as much work. So if you had a 20 coulomb charge, the same journey would cost 2,000 joules of energy. This suggests that the amount of work you're doing on that journey, the change in potential energy along this journey, is also proportional to charge. Change in potential energy is proportional to the test charge, just like how force was proportional to the test charge, and for the same reason. That means that change in potential energy can be written as test charge times something, and that something is called electrical potential, which we're going to write as V. This is the electric potential. Not to be confused with electric potential energy, which is different. I apologize for the confusing terminology. Potential and potential energy do mean different things. The electric potential is also called voltage because it is ultimately measured in volts. And this is the same voltage we saw when we were looking at electrical circuits in 7B as well. It's just that in 7B, we were looking at it confined to along wires in a circuit. Here we're looking at voltage or potential in empty space with an electric field. But these are related. The potential energy is just the voltage, or the voltage, if you solve this for voltage, voltage is just potential energy or change in potential energy divided by charge. So voltage or potential is just potential energy with the charge divided out of it. In very much the same way that electric field is force with the charge divided out of it. So for electric field, we're taking the force that is experienced by this object, dividing by the charge of that object, and any dependency on the object cancels out. We're left with electric field at that location in space, even if there's no object there. Same thing here. Change in potential energy is experienced by this object as it moves on this journey. If we divide by charge, though, the dependence on that object cancels out. So the change in voltage is a property of the journey itself. These 2 points have a difference in voltage. And we can calculate that by just dividing. Change in energy divided by charge, 1,000 divided by 10, is going to be 100 volts. So this path has a delta voltage or delta potential of plus 100 volts. Or we would say this location is 100 volts higher than this location, even if we don't put an object there. Voltage is a property of the location in space. So this would be a high voltage region, this would be a low voltage region. And note that the electric field points from high voltage towards low voltage. That's going to be universally true. Electric field points from the high voltage zone to the low voltage zone. Any other questions on that? And again, take a look at that chart I put together on math.andcheese.org/P7C. That should be a good reference for understanding the relationship between these quantities, the voltage or potential, the electric field, the electric force, and the electric potential energy. So familiarize yourself with those terms, how they're related to each other, and we will look at some more examples next time.